Hello, Chem 1. The last time we were together, we learned how to calculate a formula, an empirical formula, using a percent composition. Today we're going to use the same process to calculate formulas of a hydrate and molecular formulas. Let's get started. First, let's start with a hydrate. During Unit 6, we learned that a hydrate was an ionic crystal that had water that was embedded or trapped within that crystal. We dehydrated those crystals into anhydrous salts in lab, and we also learned how to come up with the percent composition for the hydrate. Now we're going to use that percent composition to calculate the formula of the hydrate that we don't know. And we're going to do this by finding the mole ratio between the anhydrous salt and the water that's in the hydrate. So here's a hydrate known as borax, or hydrated sodium tetraborate. You can see the anhydrous salt formula, Na2B4O7, and then you can see there's a question mark in front of the H2O molecule. That's because we don't know how many water molecules there are per unit of hydrate. So the process is the same. We divide by the molar mass to get to moles, and then we divide by the lowest number of moles to get to whole numbers. And then we use that ratio to come up with the mole ratio. So if we look at what we have here, we've taken the 52.8% and we've turned that into grams, because if we assume a 100-gram sample, it would be 52.8 grams. Then we're going to divide by the molar mass of Na2B4O7. So if you add up 2 sodiums, 4 boron, and 7 oxygen, you get 201.2. So 0.26242, that's how many moles of the anhydrous salt we have. Then you take 42.2 grams of water and you divide by 18, which is the molar mass for water. And that gives you 2.6222 moles of water. So that's our mole ratio, 0.26 to 2.6. So then we divide by the lowest number of moles so that we can get to whole numbers, and we get 1 and 10. So what do those numbers mean? What that means is that for every 1 anhydrous salt formula unit, we have 10 water molecules. So that tells us that the coefficient in front of water should be 10, and therefore the formula is Na2B4O7 times 10 to the H2O. It's telling you how many water molecules you have per salt unit. Here's another example that's got some lab data. We have a sample of hydrate at 3.73. And then we heated it and drove off 1.69 grams of mass, which would have been the water. So right now we know that this is the amount of H2O, because when you heat a hydrate, the water evaporates. What we need to figure out is the mass of the anhydrous salt, but we don't have that right now. What we have is the mass of the hydrate. So the hydrate equals the anhydrous plus the water. So what that means is, to get the anhydrous, I need to take 3.73 and subtract the 1.69. As we just said, we need the anhydrous in water, so we're going to take 3.73 minus 1.69 to get 2.04. That is the mass of the anhydrous, just the cobalt-2 chloride, without the water in it. So then we're going to take that 2.04 grams and we're going to divide by the molar mass of cobalt chloride, and then we're going to take the mass of our water and divide by the molar mass of water, H2O. You can see that we get 0.0157 moles of cobalt chloride and 0.0938 moles of water. So we divide by the lowest number of moles to get whole numbers, and this comes out as 1, this comes out as 6, which means my formula should be 1 cobalt chloride for every 6 H2O. So you can see that the process is the same that what we've done in the past. It's just applying it to hydrates. Divide by the molar mass, divide by the lowest number of moles, get your whole number ratio. Here's another set of lab data. We go through this example because it's a lot like what we're going to be doing in lab. We have a crucible and cover, and then we have a crucible and cover with a hydrate that we're going to put in it, and then we're going to heat it up and have just the crucible and cover and the anhydrous left. The reason we give you these numbers is because we want you to be able to think through how you get just the anhydrous and the water. So the difference between these two would be the water, which is what we have here. the hydrate and the anhydrous. And then if we take what we ended with and subtract out the crucible and cover, that would give us just the anhydrous salt. And at that point, the process is the same. You see that we get a ratio of 1 to 9, telling us the formula of the hydrate. So some of this is going to require some critical thinking based on the data you've been given and what you need to subtract out to get to the anhydrous and the water. All right, so that's how we do the formula of a hydrate. Now we're going to take a look at how to do a molecular formula. This would be something that does not necessarily have the lowest ratio. So for instance, if you look at benzene down at the bottom, it's C6H6, but the empirical formula would work out to be CH. So how do we calculate a molecular formula that's not reduced from an empirical formula problem setup? Just to give you some more examples, you can see the empirical formulas here are the most reduced for some of these. And then the molecular formula is the actual formula of some of these covalently bonded substances. C6H6, C2H2, here's glucose that can be reduced. Notice water, the empirical formula, and the molecular formula are the same, which can happen. So the process is pretty much the same here, except there's one extra step when you get to the end, and that would come from an additional piece of information in the problem. The additional step would be to take the molar mass that is given to you and divide by the mass of the empirical formula. And then you would know how many times the empirical formula would go into the molar mass. I know that's kind of wordy. Let's do an example, and I think it'll help you see what's going on. So here's an empirical formula problem that looks a lot like things we've done. The only difference is I'm telling you that the molar mass of this substance is 58.2, but everything else should be the same. So we have carbon and hydrogen here. We're going to take our 82.7 grams of carbon and our 17.3 grams of hydrogen, and we're going to divide them by their molar mass, so that we can get the number of moles. We get 6.89 moles of carbon, 17.1 moles of hydrogen, and we're going to divide by the lowest so we can get whole number ratios. So divide by the 6.89, and this becomes 1, and this becomes 2.5. We know when we get a 0.5 in our whole number ratio to just double everything, and that'll give us a whole number ratio. So we multiply by 2, so that this becomes a 2 to 5 ratio. What that means is the empirical formula would be C2H5. But that might not be the molecular formula. So how do we figure this out? The first thing we need to do is calculate the mass of the empirical formula. We need to know the mass of those 2 carbon and the 5 hydrogen. If we add them up, we get 29.1 grams. So now if you look at the 29.1 and you see the 58.12, you might be able to figure out what's going on here. The empirical formula mass is 29.1, but the actual mass is 58.12. So if we take the 58.12 divide by 29, we see that that empirical formula will go into the molecular formula 2 times. Meaning that we need to double the empirical formula to get to the actual molecular formula. So instead of C2H5, the actual molecular formula is C4H10. So really what you're doing is you're comparing the empirical formula that you calculate to the molecular formula that's given and seeing how many times you need to multiply by to get to the correct mass. Let's try another one. This is caffeine, something we all need on a regular basis. We got carbon, hydrogen, nitrogen, and oxygen, and the molar mass is 194. So the beginning of this process is just like what we've done. Divide each by their molar mass, divide by the lowest number of moles. When we do that, we get to the whole number ratio of 4, 5, 2, 1. 4 carbon, 5 hydrogen, 2 nitrogen, 1 oxygen. Now we need to know the mass of that empirical formula. So if we add up all those carbon, hydrogen, nitrogen, oxygen, we get 97.1. So the question becomes, how many times does 97.1 go into 194? If we divide that out, we see that it goes in there 2 times, meaning we need to double that empirical formula to C8, H10, N4, O2. I hope you can see that the process with hydrates and molecular formulas is very similar to the empirical formulas that we did last time we were together. Keep practicing all the calculations in this section. Let me know if you have any questions. We'll see you next time.